Hello there, this is Truth Socrates. Welcome to today's video where we will be learning about trigonometric substitutions. So in our previous video, we learned about trigonometric integrals where we directly see powers of sine and cosine in one integral or powers of tangent and secant together in one integral. Or maybe it's pure powers of sine or pure powers of secant or whatnot. But we have those two combinations. So in today's video, we are going to learn about integrals which are related to these because we are going to perform what's called a trig sub, trigonometric substitution, where we will end up with an integral that involves powers of sine, powers of tangent, and so on. So here are the kinds of integrals that we're going to look at. We will see integrals where we see a radical, perhaps, of the form a constant squared minus some expression squared, which involves the variable of integration, say x. Okay? So you can also have a squared plus u squared or u squared minus a squared. And you might be wondering, well, aren't these two just negatives of each other? Yes, but here we have the variable of integration subtracted, squared, but here it is a positive contribution, okay? So they're actually quite different kinds of integrals. So let me scoot this over. So here's the chart that we are going to use. It's basically a guideline for how to attack these three kinds of expressions. So this is how you read it. We're going to read it from row 1 to the last row. And we're going to read these phrases together with what we see vertically. Okay? And repeat for second column and third column. Right? So if an integral contains an expression like square root of a squared minus u squared, try the substitution, let u be a times sine theta. Okay? So a is what is squared over here. And of course, we will choose a to be a positive number. Who is theta? Theta is in the domain from negative pi over 2 to pi over 2. So that should sound familiar. Think of the arcsine function. In the arcsine function, we restricted the sine function to be between minus pi over 2 to pi over 2. So that makes this the range of the arcsine function. I hope you remember all that. Okay, so why is this a good thing? Because when you plug in u squared, you will get a squared sine squared. Okay, so you can factor out the a squared, take it out of the square root as a, and you will be left with 1 minus sine squared. Oh, but wait a minute. Everyone knows that 1 minus sine squared is cosine squared. So you will see square root of cosine squared. But you might say, okay, that's always cosine, or maybe it should be plus or minus cosine. Well, in the domain where theta is from minus pi over 2 to pi over 2, you're on the right side of the circle. Maybe I should be going like this. Right side of the circle. There, cosine is positive. Okay? So, the square root of cosine squared theta simply is cosine theta. Okay? So, once you do that, and of course, we also want to solve for du from this substitution. Okay? When you do that, you will end up with an integral that has sine, cosine, whatnot. Again, powers of sine or cosine. And hopefully, from the previous topic, we know how to attack whatever integral we get. Okay. So it's the same thing for these two columns. Okay. So let's do the last one. Okay. It's the same idea for all three. If an integral contains square root of u squared minus a squared, try the substitution u equals a times secant theta instead. So I wanted to do column 3 because we never did inverse secant theta. Okay, we never, restrict secant x and so on. So I owe you a little bit of an explanation for what we're going to do here. Okay. Secant, of course, comes from cosine. All right. Cosine is positive on the right side of the circle and negative on the left side of the circle. Okay. So what we're going to do is we're going to pick two quadrants where in one quadrant the cosine is positive and in the other one the cosine is negative, right? Now, when we did inverse cosine though, we simply picked quadrant 1 and quadrant 2. Okay, in quadrant 1 cosine is positive, everything is positive. In quadrant 2, cosine is negative. Notice here though that we are restricting theta to be in quadrant 1 or in quadrant 3. And there's a reason for that, as we're about to see. Okay, so if u is a times secant theta, then u squared will be a squared secant squared theta. Again, the a squared factors out. And you take the square root, a goes out. You're left with secant squared minus 1. But everyone should know that, well, what you remember is 1 plus tangent squared is secant squared. So therefore, secant squared minus 1 is tangent squared. So that is why we do these two restrictions. In quadrant 1, everything is positive, including tangent. In quadrant 3, tangent is also positive. Okay, so that's why we pick quadrant 3 instead of quadrant 2. To be completely honest with you, this is not going to be much of an issue because when you plug in your limits and so on, you need to stay either in quadrant 1 or quadrant 3. And most of the time, we're in quadrant 1. Okay, so don't let this scare you. All right, so in the square root, we're going to get square root of tangent squared. But since tangent is positive or 0 on those two quadrants, we simply get tangent of theta. All right, so here's how you actually execute a trig sum. First of all, you need to identify the form. So is it a constant squared minus a variable squared, or both of them are plus, a constant squared plus variable squared, or is it the variable squared minus a constant squared? So you remember the video where we did completing the square? Sometimes you might need to do that because you might have just a u term here or here or here. Okay? Don't forget completing the square. Once you do that, who is your a and who is your u? All right, so identify them and write them down. Sometimes u is simply the x. So once you have decided on that, write down the trig sum. So go back to the table and pick, is it a times sine, a times tangent, a times secant, whatnot. Next, just like in a regular u substitution, you need to transform all the parts of the integral until all the x's are gone, the u's are gone, only theta remains. The original variable for the integration should be completely gone. Gone. Included in this transformation is, don't forget your du. Never ever forget the differential. If you're looking for a definite integral, I strongly recommend that you also change the limits of the integral. Okay, so we've done that before in u sub, change the x's, the x values to u values and so on. This time you need to change the x values into theta values. Now, because we are doing sine or tangent or secant, you might need an inverse sine or an inverse tangent. What about the inverse secant? We never talked about that. So again, because we're staying in only one quadrant, you could stay with just inverse cosine. So solve for secant, take the reciprocal that gives you cosine. Now you can use inverse cosine. No big deal. Once you do all that, x is gone, u is gone, all you have is theta. And again, you will see sine theta, tangent theta, secant theta. Now you know how to integrate because in our last video, we learned how to attack those kinds of integrals. Haha! So if you're looking for a definite integral, you can now plug in the limits because you changed all the x limits into theta limits. You now have, just plug in the upper limit and the lower limit and so on. But if you are looking for an antiderivative, there's more work to be done because you are going to get an antiderivative in theta after you perform this integration. But our original integral is in x or u or something like that, okay? So theta has to go away to be replaced by x or whatever that original variable of integration was, okay? So in order to do that, it might be useful to draw a triangle. We know from trigonometry that sine is opposite over hypotenuse, tangent is opposite over adjacent, and so on, okay? So once you solve for sine theta, you'll get a fraction. You will think, okay, so that fraction represents opposite over hypotenuse and so on. Label the triangle, two sides of the triangle, solve for the third side using, voila, the Pythagorean theorem. Okay, we're going to do 4 examples, and here's our first one. I want the definite integral from 3 to 4 of radical 25 minus x squared all over x squared dx. And, oh dear Maple, what is the answer? It is approximately 0.3. Okay? Maple could have given us the exact answer, but I'm not going to show it to you because it's going to be different from the answer that we're going to get. Sometimes Maple does that. So it's more useful to see the approximation and use it to check our answer. So this is the top of the table from our first page. And our first step is to identify the form of the square root. Okay? That's a constant squared, 5 squared, minus variable squared, x squared. So obviously it is the first form. Our u is simply x, right? So as I said earlier, sometimes the u sub is actually just the x. So here, a is 5 and u is x. Okay, u is simply x. So we use u, which is x, and we want it to be 5 sine theta. Okay, u equals a sine theta is the trig sub for this problem. All right, so we don't need that table anymore. We'll just let it scroll down as we get more space. So let's work on the radical. Who is radical 25 minus x squared? And why does all of this work? So x is 5 sine theta. So we're going to get 25 sine squared theta when we square that. Okay, so 25 sine squared theta. Earlier I said the a squared is going to factor out. So now we see it. There's a 25 here and a 25 there. So we can factor that out. I'm going to use square brackets. And don't forget, the first 25, when you factor it out, there's a 1 there. It's not 0. Okay? 25 over 25 is 1, not 0. And this minus 25 goes away. All right? So we get 25 times 1, 25 minus 25 times sine squared. It works. So now we can take the square root of 25 outside as a 5, and inside we will simply get 1 minus sine squared. And now we see why it works. We will get cosine squared inside the radical. 1 minus sine squared is cosine squared. And because our our theta is between minus pi over 2 and pi over 2, I mentioned earlier, that's where cosine is positive. So the square root of cosine squared is simply cosine theta. So we can erase the square root, we can erase the square. There you go. So we have the numerator. That numerator is simply 5 cosine theta. Okay, let's do the dx next. Remember, do not ever, ever, ever forget the differential. X is 5 sine theta, so dx is 5 cosine theta d theta. Okay, so there is our d theta. Notice that previously, when we have a u substitution, like u equals, let's say u equals x squared, you will get du is 2x dx, and then we solve for dx. Notice here, dx is already solved for us because we started out with x equals something. So dx is right here. There's no need to solve for d theta. We already have dx. And in fact, we don't solve for d theta because we want to replace the dx over there. And here it is. All right, so we got that. How about the x squared now? And so from our previous equation, x squared is 25 sine squared theta. Okay, kind of looks familiar. We kind of saw that over here. Yeah, because we have an x squared over there. Duh, it's right there already. How about the limits? When x is 3, what do we get? So 3 equals 5 sine theta. Okay, so we are using this equation, which came from here, of course. So I plugged in 3 equals 5 sine theta. So who is sine theta? Sine theta is 3/5. Use the inverse trig function. And so theta is arcsine of 3/5. Okay? So similarly, when x is 4, we get 4 equals 5 sine theta. So sine theta this time is 4/5. And theta is arcsine of 4/5. Yeah. All right. So that's everything. We have computed this, dx, x squared, and the limits. So we're ready. We are so ready. We have this equals, so now that we have the problem written down, I can scroll up. This will be, let's start replacing. 3 becomes arcsine 3/5. 4 becomes arcsine 4/5. Square root of 25 minus x squared. Whoops, my bad. It's right there. Let me scroll down properly. There it is. It is 5 cosine theta. So we replace this with 5 cosine theta. Our dx is another 5 cosine theta, but it comes with a d theta. Whoops, scroll down too much. And our x squared, there it is. Good, we got everything right here. 25 sine squared theta. Okay, so let's start simplifying. I hope you see what I see. I see 25 here and the 25 there. So those constants go away. Bye-bye. And we see cosine and cosine, so that's cosine squared. So let's do that, shall we? Okay. So cosine squared over sine squared. I hope you're thinking what I'm thinking. Lunch. No, just kidding. Cosine over sine, that is cotangent, right? So this is integral of cotangent squared theta d theta. Oh no, do we know the integral? Let me just do that. Do we know the integral of cotangent squared? We know the integral of cotangent. Remember that one? Negative ln of absolute value of cosecant. Drove many of you crazy. Why is there a cosecant? It's cotangent squared, though. We did do tangent squared in a previous video. I hope you remember. If you don't, that's okay. What did we do with tangent squared? Well, 1 plus tangent squared is secant squared. So secant squared, so tangent squared is secant squared minus 1. We know how to integrate secant squared. We know how to integrate 1. Okay? So, same idea. What is the Pythagorean identity? 1 plus cotangent squared theta is, anybody? Yes, hopefully you remember, it is cosecant squared theta. Okay, and we know how to integrate cosecant squared theta. So cotangent squared theta is cosecant squared minus 1. Okay, so we're up here, and we get, this will be integral of cosecant squared minus 1. Okay, so integral of cosecant squared is cotangent, no, negative cotangent. Okay, the derivative of cotangent is negative cosecant squared. So the integral of positive cosecant squared is negative cotangent. And the minus 1 becomes minus theta. We evaluate from the lower limit, arc sine of 3/5, to the upper limit, arc sine 4/5. Let me just change that to a 4. All right, so we have to plug in the limits. However, we want cotangent theta. Okay, so let's do that separately. Okay, so let's give it a name. Let's give the angle a name. Let alpha be arc sine 4/5. Okay, so we have a triangle. Okay, opposite is 4, and hypotenuse is 5. Okay, so adjacent, so remember the Pythagorean theorem. So sorry, I'm not going to draw a triangle for you. You can do it in your notes. Opposite 4, hypotenuse 5, Pythagorean theorem, 25 minus 16, 9, square root of 9 is 3. So adjacent is 3. Okay, we want the cotangent. Cotangent is, all right, so tangent is opposite over adjacent. So cotangent is adjacent divided by opposite. Okay, so we have 3 over 4. Okay, got it? Similarly, for the lower limit, for beta equals arc sine 3/5, what are we going to get? Oops, sorry about that. Edit, undo, paste. I hate it when I do that. So arc sine 3/5. So opposite is 3. Hypotenuse also 5. And adjacent equals 4. So cotangent beta is adjacent over opposite. So 4 over 3. It's the reciprocal. All right. So we are ready. We are ready. Are you ready? Let's bring that down here. So in the upper limit, we need negative cotangent, so minus 3/4, and then minus theta. No choice, we will just write minus arc sine 4/5. That's okay, that represents an angle. Okay, minus bracket, be very careful because you have very dangerous minus signs here. So we have negative, we got out of the way here. We have negative cotangent, so we have minus 4/3, minus 4/3 here. And then minus theta, so minus arc sine 3/5. All right, there we go. So we just need to clean this up now. The first part doesn't change. you do have minuses there. And again, those minuses bite. So be very careful. Minus 4/3 is plus 4/3. And minus arc sine is plus arc sine of 3/5. All right. So we have 4/3 minus 3/4. Yeah, fun with fractions. 4/3 minus 3/4. So that's 16 minus 9 over 12. 16 minus 9 over 12. 7 over 12. And, ooh, yeah, haha. And these two angles, plus arc sine 3/5 and minus arc sine 4/5. All right, so our final answer, which is simplified fraction of kills, that is simply 7 over 12 plus those two angles. That's the exact answer. Earlier, we had an approximation. It's about 0.3. So please keep your fingers crossed. Are we correct? What's that approximate value? Yep, that's exactly the same decimal approximation we got earlier. I win. Haha. Our second problem. Sometimes you don't even need a trig sub, even though it is so tempting to use one. Okay, so we have a variable squared minus constant squared. Looks like we could use secant theta. Yes. Yeah, we have this x in the denominator though. So what's the idea here? We're not going to use a trig sub. We're simply going to use an ordinary u sub. So be brave. If I said, hint, you can do this with just a simple u sub. The guiding principle for u sub is almost always make the ugly part go away. So this is the ugly part. Make that your u. So in this case, du is just 8x dx. Okay? And that's good because now dx is 1 over 8x du. So let me put a fraction, 1 over 8x du. Okay? So that's good because we have the square root, we have the x. What about this other x here? Okay, so let's leave that alone for now. But hopefully you're saying to myself, wait a minute, this feels familiar. Kind of happened in our very first video when we did u subs where, yeah, parts of it did not quite fit until you put everything together and like, oh, I know what to do with that one. So this is our u, so we changed that to a u, and our dx is 1 over 8x du, so we changed that as well. And now something nice happens, something very convenient happens, because this x can merge with the 8x to make 8x squared. Ooh la la. And that is awesome because I see a 4x squared here. I want 8x squared. So, but u, why am I typing it? It's right here. U is 4x squared minus 9. So u plus 9 equals 4x squared. And I want 8x squared. So, pardon the interruption. Where were we? I wanted 8x squared, so 8x squared. Oops, it should be in math. 8x squared is twice of u plus 9. Okay, that's good. So we stopped here. We can replace 8x squared with 2 times u plus 9. Okay, so our integral becomes this by just a simple u substitution. Okay, this is this. I need an integral sign. Okay, I'll just keep that and I'll replace with this. Okay, we still have a little problem though. Okay, how do we integrate this? Okay, so let me show you something a little clever and not very obvious. Okay, 9 is of course a perfect square. It would be nice if this were u squared, maybe, because remember what we did for the arctangent function. Okay, so here's the clever thing that we're going to do. We're going to do a second substitution. U is the square, yes it is, a square of square root of u, right? So v squared is u, and we want u plus 9, v squared plus 9 is u plus 9. Okay, so this becomes something familiar, v squared plus 9, but what about the 1 over square root of u? Check it out. If v is square root of u, which of course is u to the 1/2, we still need dv. So dv is minus 1 u to the minus 1/2 divided by minus 1/2. So I need a fraction. Where will I borrow a fraction? How about over here? U to the minus 1/2 divided by minus 1/2 times du. Oops, not dx, but du. So we need du. It will be, yeah, you know what? Let's clean this up first, because all these minuses are annoying, right? And the reciprocal in the denominator too. So that is 1 over negative 1/2. That is simply negative 2 in the numerator. And the u to the minus 1/2 in the numerator becomes u to the plus 1/2 in the denominator. Okay, that's less crazy, right? So, solve for du. It is, bring the u to the 1/2 over, and we have the dv, and everything is divided by negative 2. Okay, there we go. So we are now ready to transform this. So we get square root of u. Okay, so that square root of u is our v. Thank you very much. We said that u plus 9 is v squared plus 9. Oops, what did I edit and paste? V squared plus u plus 9 is v squared plus 9. And du is u to the 1/2 dv over negative 2. Yay! Oh, but wait a minute. U to the 1/2 is square root of u. That is also v. So these v's cancel. Yay! And we have dv over negative 2, so that negative 2 can join the 2 here to become negative 4. All right, so we get negative 1/4. I'm going to borrow this. And the v's have vanished, will vanish, and we are left with only 1 over v squared plus 9 inside our integral. Yeah, let me start fresh here. 1 over v squared plus 9 dv. Yay! So now we know how to integrate that, right? So we factor out the 9. It's like we're going back to our first video, almost. So we factor out the 9, and we will get 36 outside. and we will get v squared over 9 plus 1. And then we do another small substitution this time. Let w be v over 3. So dw is dv over 3, and dv equals 3 dw. So this becomes v squared over 9 is w squared, dv is 3 dw. All right, so we lose one of the 3's, so we're down to 12. Just one equal. 12 integral of 1 over w squared plus 1. So of course that is the arctangent of w. Yay! All done. Oh, but we have to go back all the way to x. Okay, so we have an indefinite integral. Yeah, not a definite integral. So we have to trace our way back. Who is w? It is v over 3. So w is v over 3. Who is v? V is square root of u. So v becomes square root of u. But who is you? Who are you? Who are you? U is higher. It's back here. 4x squared minus 9. All right. So let's set that down here. So this becomes negative 112 arctangent of square root of 4x squared minus 9. All right. And if you like, you have the ubiquitous plus c. All right, so the last example did not require a trig sub because it was an x here, and we were able to get rid of it with some magic, just use substitution. If it's an x squared, though, we're going to have an extra x, and based on that use substitution, it's going to be nasty solving for x in terms of u. So we are better off actually doing the u sub for this problem. So again, we have variable squared minus constant squared. So that's this form. Okay, so we're going to do the last one with the secant theta. Okay, so in this substitution, we have u is 2x, variable squared. So it's 2x quantity squared makes 4x squared. And our a is 3 squared to give you 9. Okay. 4x squared, 2x quantity squared, minus 9, 3 squared. So we use this substitution. So we use u equals 2x equals a 3 secant theta. There we go. So that is the sub that we need. Okay. Replace. This 2x squared, so 3 secant theta quantity squared, which is of course 9 secant squared. Squared belongs there, looks nicer. Once again, the 9 can factor out, so secant squared, and once again, that minus 9 leaves a minus 1, not 0. It doesn't just disappear, okay? 9 quantity secant squared minus 1. The square root of 9 goes out as 3. And inside, we are left with secant squared minus 1. 1 plus tangent squared is secant squared. Tangent squared is secant squared minus 1. So this is square root of 3 square root of tangent squared theta. So again, this is the one with the weird restriction. We are in the first and the third quadrant. So the tangent is positive in those two quadrants. We simply get 3 tangent theta. Let's do it on the next slide. 3 tangent theta. Excellent. Once again, so this time, not once again, we have an x squared. This is 4x squared. So careful, solve for x first. X is 3 secant divided by 2. So let's write an actual fraction. 3 secant theta divided by 2. So x squared is 3 squared becomes 9. 9 secant squared, 2 squared is 4. Let's do the dx on the same line. And dx is, so we have this, the derivative of secant is secant tangent. Right on, 3 secant theta tangent theta, don't forget the d theta. Okay, never ever ever forget the differentials. All right, I think we got everything. We got x squared, we got the square root, we got the dx. Ready to plug it all in. X squared, replace. Square root of 4x squared minus 9 is 3 tangent theta. Replace. Dx. This guy over here. Okay, so be very, very careful as we simplify. Okay, deep breath, deep breath. So let's make a copy of that. What do we see? Well, there's a 3 tangent here and also a 3 tangent here. So let's get rid of that. That instantly makes it a lot shorter. So the tangents are gone. Oh, that's nice. We have a 2 here and an over 4 here. If this makes you uncomfortable, I don't blame you. You can flip it up first and then cancel with the 2. Okay, let me get out of the way here. So we get, this goes away, that becomes 1, and this becomes 2. And the 2 goes up. Secant, all right, so secant squared, so that also goes away, and you're left with a single secant. So, wow, a lot of it went away, and we will flip the 2 into the numerator, so we get 2 over 9, new fraction, 2 over 9, which we can take outside, and we have integral of 1 over secant. Oh, wait a minute. That's just cosine. Ooh, excellent. D theta. And we all know that one. That one's easy. Integral of cosine is sine theta plus c. Okay, we're done. No, we're not done. We are far from done because that's in theta. We started out with an x. Okay. So here's the problem. We have secant theta. We want sine theta. Okay. So this time I will actually draw you a triangle. We're going to go to paint in a minute. Okay. So let's copy this. This is the Rosetta Stone that will enable us to find sine theta. Okay. 2x is 3 secant theta. So secant theta is 2x over 3. 2x over 3. Okay. So secant is 1 over cosine. but cosine is adjacent over hypotenuse. So we want hypotenuse over adjacent. Okay? So we're going to draw a triangle, and in the triangle, the hypotenuse will be 2x, and the adjacent will be 3. All right, so I'm going to call up paint, and we're going to draw a triangle. All right, so here we are in paint. We're going to draw a triangle. So we have a vertical side, and we have a horizontal side, and we have a hypotenuse. Okay, so we'll just pretend that they're all connected to each other. Okay, so we said that the hypotenuse is 2x, so let's start typing. The hypotenuse is 2x, and the adjacent is 3. And of course, this is our angle theta. Okay, so I'm just going to write theta. Yeah. Okay, so on the opposite, we need to complete a triangle. So Pythagorean theorem, square root, I'm going to be lazy here, square the hypotenuse, so 4x squared, and then subtract adjacent squared, so that's minus 9. Okay, and I'm deliberately just putting paint on top of our work so far because check it out. Haha. The original radical appears. Square root of 4x squared minus 9. Okay? Because what did we want? We want sine theta. Is that right? Let me remove this. Oh yeah, there it is. We want sine theta. So sine theta is opposite over hypotenuse. All right, so we have the original square root divided by 2x. Okay, so I don't even need to pause our recording. We can continue here. This is negative 2/9, and we have, I'm sorry, there is no negative. So we said that the opposite is our original radical, and our hypotenuse was 2x. Oh, check it out. Something nice happens. So the 2's vanish, and in fact, I just need one fraction. So we're going to get 9x in our denominator. The 2's disappear, and we simply get 9x, and of course the square root in our numerator. Yay! Okay, so usually when I'm recording these videos, my screen is only up to here. I don't show you the taskbar up here, but I want to show you that our answer is correct and how to do it in this taskbar. There's an equal sign here that tells Maple, okay, tell me what that integral is. And there it is. Okay, so I'm not just cutting and pasting the correct answer. When I click a button, it really is what we did find, okay, which is of course down here. Okay, same answer that we got. All right, now we've done examples where we see a square root, and that's really where the power of a trig sub comes in. But it's also powerful even when there's no square root. All right, so instead of 1/2, we have 2 power 2 square. Okay, so no square root there at all. But let's try a trig sub. Constant squared, variable squared. So plus plus. Okay, so there's only one plus plus combination. That's this one. Right? So identify. A is 4. 4 squared is 16. And U is 3x. 3x squared is quantity squared is 9x squared. So we use U is 3x is A 4 times tangent theta. Okay. So now we don't have a square root. We just have this. So 9x squared is 3x quantity squared. And we said that 3x is 4 tangent theta. So square that, we get 16 tangent squared theta. Again, 16 factors out, but there is no square root where we will take it out. So just keep it as 16. There is no square root. 1 plus tangent squared is secant squared. So we get 16, secant squared. Once again, there is no square root. However, so we have this, so we're going to square it. But there's more. We also need 3x plus 7. Oh, how convenient. That's a 3x. So 3x plus 7. I didn't actually intend that, but it's okay. It keeps us from avoiding fractions, from dealing with fractions. So 3x plus 7 is 4 tangent theta plus 7. Okay, so if it was 3x plus 5, I'm sorry, if it were 4x plus 7, let's say, then you'll have to solve for x and then plug it in, okay? Just avoiding some complications. Okay, but we also need dx. So we take this down. So take the differential, 3 dx equals 4, derivative of tangent is secant squared. Secant squared theta d theta. So dx is 4/3. I need a fraction. 4/3 of secant squared theta d theta. Okay. So you know what? We need squares, a square in the denominator. So let's go ahead and also get the square. Square the whole thing. So this is 16 secant squared squared. Wow. Oops, sorry. Don't get mad at me, Maple. Squared. 16 squared is 256. And secant squared squared is secant to the power 4. All right, I think we got everything. Time to plug them in. Three x plus 7 is 4 tangent theta plus 7. Denominator is 256 secant to the 4th power. Dx is 4/3 secant squared. Place. Okay, all the x's are gone, including dx. We are left with just thetas. Simplify. Okay, so I see a 4, we got 256. 256 divided by 4 is 64. And that goes away. Secant squared, ooh, there's a secant squared here also, so that goes away. And that's just secant squared. Okay. So, yeah, the constants, well, I guess we don't have much we can do. We will take the 1/3 out and the 64. What is 64 times 3? 4 times 3 is 12, 18, and 1 is 19. So 192. And we get, so we took the 64 out. Oh, interesting. Very interesting. So we just took out the constants there because what I want to do next is let's bring secant squared into the numerator. Okay, because 1 over secant is cosine. So there's a cosine squared in our problem, but it's in the numerator. So I will turn the secant squared into cosine squared. And we're going to keep this. And we better put brackets here. Okay, this is getting interesting. Because what we're going to do is we're going to distribute that cosine squared. So we get tangent times cosine squared plus 7 cosine squared. So 4 tangent theta cosine squared plus 7 cosine squared theta. All right. So why is this good? Well, it's because tangent is sine over cosine. So sine over cosine times cosine squared. 2 of the cosines cancel, leaving a single cosine in the numerator. So this simply becomes 4 sine theta cosine theta. And that's good. That is not hard to integrate at all. 4 sine theta cosine theta. Okay. You know what to do with cosine squared? You remember? You remember? Power reduction formula. Cosine squared is 1 plus cosine 2 theta. What? I have to remember all of that? Yes. In a word, yes. Okay. And so, yeah, we can just split that up as we usually do. So it becomes 7 halves, and plus 7 halves cosine 2 theta. And cosine 2 theta. All right. So we are ready to integrate. Break it up into 3 pieces. Okay. For the first piece, we will let u be sine theta. So du is cosine theta d theta. Whoops. Why is there a big parenthesis here? I forgot to get out. Du is cosine theta d theta. So that's easy. And for the third, second is only a constant, we will let v be 2 theta, and dv is 2d theta. Oops, I'm sorry. 2d theta, and d theta is 1/2 dv over 2. Okay, so you get 1 over 192, and we have a bunch of integrals. Okay, so we have integral of 4. Our sine theta is our u. Our du is cosine theta d theta, so that's 4u du. Plus 7 halves. 7 halves, we don't need a formula. Well, we don't need a sub for that. We just get theta. There's still a theta there. Okay, it's not 0. There's a theta there. And then for the last one, so we get cosine 2 theta is, so we get cosine of v, and d theta is dv over 2. So we get a 1/2 plus 1/2 integral of cosine. So by the way, this still needs to be integrated. And this third one, we only integrated the second term. So we get 1/2 cosine v dt. Okay, so now we are ready to integrate the first and the third. Now, if you're doing this on your own, it will be a good idea to complete the integration and then assemble it all together. Okay, so our first integral, you'll get u squared over 2, so you will simply get 2u squared. And for the last one, we will get 1/2 sine of v. The sine is cosine, yes. So that is 1/2 of sine of v. Okay, oh, but wait a minute. Our v is 2 theta. Oh yeah, and our u is sine theta. Yay, so we have sine squared theta. And our sine of v is, 2 theta. Yeah. Okay, now, so remember when we did power reduction, yeah, we get double angles. Now remember, we still have to go back to x because, check it out, we have an indefinite integral. So all the thetas will have to go back to x. And again, our Rosetta Stone is this substitution. So let's copy it down here because we will need it to go back to x. Okay. Yeah, so we're just going to do one more step, okay, because we have a double angle here. Let's use the double angle identity. Sine 2 theta, I hope you remember, is 2 sine theta cosine theta. Okay. You might be tempted, by the way, to do a power reduction here. You don't need it. We already integrated. Okay. So this simplifies to just sine theta cosine theta. Okay. So we have this sub, and we are going to use it to go from theta back to x. And again, this is the key equation. So tangent theta is 3x over 4. 3x over 4. Triangle. So once again, label the sides. Tangent is opposite over adjacent. Opposite over adjacent. So our opposite is 3x. Our adjacent is 4. Okay? I'm not going to hop back to paint. I'm going to let you do that. So instead, we'll do the Pythagorean theorem here. Okay? We already have opposite and adjacent. We're just missing the hypotenuse. Hypotenuse is directly square root of opposite squared plus adjacent squared. 3x quantity squared plus adjacent squared. Oh, check it out. What is that? 9x squared plus 16. Sounds familiar? Did we see 6 squared plus 16, 9x squared plus 16 before? Oh, there it is. Okay, we have 9x squared plus 16. It is part of the original integral. So as I always say, when you're doing these trig integrals, integrals with a trig sub, you should almost always see the source of the trig sub appearing in the final antiderivative. Okay, so it's about to pop out. Okay, so that's the hypotenuse. We want sine and cosine, so that's fine. Oh, we also need theta. All right, well, theta, of course, we will need an inverse tangent function. So theta is arctan of 3x over 4. Okay, so we're almost done. Famous last words. So we have 2 sine squared. So sine, we'll replace this, something squared. Fraction. Sine is opposite over hypotenuse. Our opposite is 3x. Our hypotenuse is this, 16 plus 9x squared. Okay, there we go. Our theta is arctangent 3x over 4. There we go. Sine theta. Oh, we already have sine theta over here. So, thank you. Cosine theta, though, is adjacent over hypotenuse. All right, so that's already our hypotenuse. All we have to do is change opposite to adjacent, which is 4. Okay. So there we go. This is just about finished. Okay, so if you were taking a test or something, you will be breathing a sigh of relief at this point, saying, "Ah, thank God I'm done. I can move on to the next problem. There are another 20 problems." Just kidding. So, but if this was in your homework problem, this will not be the final answer because it can obviously be simplified. Okay, so we're squaring. So we're squaring the numerator and the denominator. We get 9x squared, but there's a 2. So that's 18x squared. So I'm going to erase the square. That should be 18x squared, and we got the 2 accounted for. One more time. 3x quantity squared, 9x squared times 2. We get 18x squared. Isn't it a good idea to review your work? Okay. I missed that square. I will take responsibility. So this is bracket squared. But check it out. You also have 2 of the hypotenuses over here. So that is also a square. Okay. And we have 4 times 3x here. So that is 12x. We only need one fraction. And, oh wow, same denominator. So of course you know what's coming. We are going to combine those 2 fractions into a single one. 18x squared plus 12x divided by 16 plus 9x squared, quantity squared. Okay, so we have that, and we can erase this. Whew. Okay, yes, my apologies. Another long video, big surprise. You saw the timestamp when you opened it up. So I hope you were pressing pause and taking breaks and going to the refrigerator, see if there's anything new inside. That's our video for today. Thank you so much for watching. Until next time, I hope you enjoy the rest of your day. Bye.